So one of the things about the central limit theorem is that the original distribution that you're looking at does not have to be normal. The video that we watched on Tuesday, the original distribution was normal, because if you look at heights of human beings, the height of human beings will be normally distributed. So they were able to take samples of 4 small samples, and they were able to take all the different combinations of samples of 4 from that group of children, and then look at the distribution of the sample means. So that's what they did. And it's normally distributed no matter what the original distribution looks like. And it's normally distributed with a mean that is the same as the population mean. But the standard deviation is narrowed. Since you're looking at a distribution of means, they're clustered closer to the actual population mean, which means you have less variance. So the standard deviation is smaller. So what I was doing yesterday, and then I decided it probably wasn't worth demoing, but I was looking at rolling a die. So if you roll 1 die, you would expect the probability distribution to be uniform, because you would expect the probability of getting a 1 would be the same as the probability of getting a 2, which is the same as the probability of getting a 3, etc. Correct? You would expect each one of those to have a probability of 1/6. But if you roll 2 die and then take the average of those 2 die, so you take the sample average, then it becomes a little bit more normal. And if you start rolling like 30 die and taking the average and looking at the distribution, then it becomes normal, which is kind of cool. So that's all we do in chapter 7. We're only covering the first section on discussing the central limit theorem, which means the central limit theorem says that no matter what your population distribution is, if you take samples from that population and look at the mean of that sample, and then you look at the probability distribution of the sample means, it will be normal. And depending on how unnormal your original population distribution is, you may have to take larger samples. So for example, the one we looked at, the video where they were talking about the phone, length of phone calls, that was incredibly not normal. So when they started taking samples, I don't know if you noticed, they took samples of 50. So their sample mean was based on a sample size of 50, so it had to be larger. The samples have to be of larger size if your population is not normally distributed. Okay, so that was what I was doing. So I was rolling 2 die, then 3 die, then 4 die, then 5 die, then 6 die. No, 5 was as much as I got, and then taking a distribution of the sample means. So that was what I was doing here. This right here is a distribution of the sample means. Okay, so we'll look at this graph here in just a second. So the central limit theorem. The central limit theorem, CLT for short, is one of the most powerful and useful ideas in all of statistics. There are 2 alternative forms, and both alternatives are concerned with drawing finite samples of size n from a population with a known mean and a known standard deviation. The first alternative, which is what we concentrate on, says that if we collect samples of size n, with a large enough N. So the large enough N means that you have to draw a larger sample if your original population is not normally distributed. If your original population is a normal distribution, then it really doesn't matter so much what the size of your sample is. Anyway, the first alternative says that if we collect samples of size N with a large enough N, calculate each of these samples mean, and then draw the histogram of those means, the resulting histogram will be normal. The second alternative says that if we collect samples of size N that are large enough and we calculate the sum of each sample and create a histogram, it will be normally distributed. We normally, that's not probably enough, typically look at sample means and not the sum of the sample. And for you, practically, the only difference in section 7.1 compared to 6.2 is what you use for the standard deviation. Since you're looking at sample means, the distribution of sample means, you will not use the population standard deviation. You will use this population standard deviation divided by the square root of N. Uh-oh. And this is an example if you were to sum. If you wanted to look at how much change people carry in their pocket, you could take a population and you could take samples of that population and just count how much money they have in their pocket. Does anybody carry change anymore? I have some in my purse, and then I usually, when my purse gets full, I go dump it. But I don't normally pay anything with cash anymore. Use a card for everything. So again, the central limit theorem for sample means says that if you repeatedly draw samples of a given size, such as repeatedly rolling 10 die, and calculate their means, those means tend to follow a normal distribution. As the sample size increases, the distribution of means more closely follows the normal distribution. The normal distribution has the same mean as the original distribution and a variance that equals the original variance divided by the sample size. So since standard deviation is the square root of variance, the standard deviation of the sampling distribution is the standard deviation of the original distribution divided by the square root of N. The variable N is your sample size. It's the number of values you're averaging together, not the number of times the experiment has been done. Okay, so again, practically, what's the difference in what you did in 6.2 and what you're doing in 7.1? It's the standard deviation you use. If you're looking at the distribution of sample means, you have to use the standard deviation of the population divided by the square root of N. So suppose X is a random variable with a distribution that may be known or unknown. So I don't know what the distribution of the original population looks like. Using a subscript that matches the random variable, we let mu sub X be the mean of X and sigma sub X equal the standard deviation of X. So if we draw multiple samples size N from our population and we look at the distribution of the sample means, it will be normally distributed with a mean that is equal to the population mean. But a standard deviation, that's the population standard deviation divided by the square root of n. And this is my experiment I was doing yesterday. I did it in Excel and it didn't, Excel just will not draw a good histogram. So I did it in Excel and then I did it on my calculator, and my calculator did much better. But since my calculator is limited by the number of lists I can have, the most number of die I could roll at one time was 5. So I had each of my first 5 lists were random numbers between 0 and 6, no, 1 and 6. And my 6th list was the average of the first 5. So if you roll 1 die, you would expect that the population distribution, the probability distribution, to be uniform. Each face has the same probability of occurring. But if you roll 2 die, and then you take the 2 faces and you find the average, and you look at that distribution, it starts looking more normal. And as you increase the number of die you roll, and you find the distribution of the sample means, it becomes normally distributed. So this is 10 die. Rolling 10 die, adding the faces together, dividing by 10, and then plotting that average. So the distribution of the sample averages is normally distributed. Okay. To put it more formally, if you draw random samples of size n, the distribution of the random variable x bar, which consists of the sample means, is called the sampling distribution of the mean. The sampling distribution of the mean approaches a normal distribution as the sample size increases. And yeah, that was it. Okay, so again, you're going to use your normal CDF on your calculator. The mean will be the mean of your sample, which is also the mean of your original distribution, but the standard deviation will be the population standard deviation divided by the square root of n. And you can type that into your calculator, sigma over the square root of n, and it will calculate it for you. And I'll show you what I mean just here in a second. Okay. In a recent study reported October the 9th, 2012, I don't know if that's recent anymore, not very recent, is it? On the Flurry blog, the mean age of tablet users is 34 years. I suspect that's not true anymore, because we've all gotten older. You know how many tablets I have? Got this, I got 2. Suppose the standard deviation is 15 years. Take a sample size of n equals 100. What are the mean and standard deviation for the sample mean ages of tablet users? Okay, so they tell me that the mean age of my population is 34 years. So the mean of my sample mean will also be 34. So I would use a mu of 34. But the sigma I'm going to use is going to be what? It's going to be the standard deviation of my population divided by the square root of my sample size. So again, because I'm looking at the distribution of sample means, the standard deviation of the distribution of sample means is smaller than the distribution of my population. So what would that be? 1.5. So if I were to be finding some probability for this distribution, which I am going to do here in a minute, on my calculator, I would use mu 34, but I would use sigma 1.5. If you were looking at just the distribution, if this is normally distributed, if you were just looking at the distribution itself, you would use a mu of 34 and a standard deviation of 15. Okay, in a recent study reported October the 29th, 2012 on the Flurry blog, the mean is, again, what does the distribution look like? Well, I don't know what the distribution of the original population looks like. I don't know if the average age of the population is normally distributed. But I do know that if I look at multiple samples of from the population, size 100, and I find the average age of each of these samples, and I look at the distribution of the sample means, it will be normally distributed. So even though I don't know the population's distribution shape, I do know that the distribution shape of the sample means would be normal. And sample size 100 is a good sample size. All right, so now let's find a probability. Find the probability that the sample mean age, so as soon as I see this, I know I'm going to be using the central limit theorem because I'm looking at sample means. And since I'm using the central limit theorem, I'm going to use a standard deviation of 1.5. Otherwise, it's just like I did before. So what am I looking? More than 30 years? More than 30, is that right there? Does that look like that? More than 30? Okay, so on my calculator, what do? So I would do a normal CDF. What's my lower limit? Is that 30? What's my upper limit? A really big number. What's my mean? 34. What's my standard deviation? 1.5. So depending on your calculator, so I'm going to go normal CDF. My lower range was 30. My upper range is going to be a really big number. My mean was 34. And you can actually type in 15 divided by the square root of your sample size. You can actually type that in and your calculator will calculate it for you. I mean, that's a pretty easy one to calculate. Sometimes they're not so easy. So your calculator can do that for you. So when you take it back into the home screen, this is what it would look like. Normal CDF, 30, comma, big number, comma, mean, comma, standard deviation. Did you get 0.9961697? Is that what you got? and I don't mean to keep repeating this over and over and over again, but last semester, the most common issue I saw was with what standard deviation you use. If you're talking about samples and their means, you have to use the standard deviation, that is the population standard deviation divided by the square root of n. Okay, an unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equals 25 are drawn randomly, I can't read, from the population. Find the probability that the sample mean is between 85 and 92. I'm a picture drawer, I have to draw pictures. Okay, since I'm talking about sample means and not the population, then what am I going to be doing here? So my mean is still 90, but my standard deviation will be the standard deviation of the population divided by the square root of the sample size. So what am I looking for? Between 85 and 92? So 85 and 92. Is that the area under the curve that I'm looking for? So what would that be? That would be normal, CDF. My lower limit was 85. My upper limit is 92. My mean is 90, and my standard deviation is 15 over the square root of 25. Yeah, you could calculate that. That's going to be what, 3? It's a pretty easy one to calculate. I'm going to go to my calculator and go to my normal distribution. My lower limit was 85. My upper limit was 92. My mean was 90. My standard deviation was what? 15 over the square root of 25. 15 divided by square root 25. So normal CDF 85, 92, 90, 15 divided by the square root of 25. 0.6997, is that what you got? Find the value that is 2 standard deviations above the expected value 90 of the sample mean. So what value would be 2 standard deviations above the mean? Well, if we're talking about sample means again, the standard deviation is the standard deviation of the population divided by the square root of the sample size. So we said that was 3. So 2 standard deviations would be 2 times 3, which is 6. So what's 2 standard deviations above the mean? 96. What would be 2 standard deviations below the mean? Would that be 84? What would be 3 standard deviations? Would that be 9? So 3 standard deviations above would be 99. 3 standard deviations below is 81. You would expect most of the sample means to be between plus or minus 3 standard deviations. Correct? Because your empirical rule says, what is that, 99.7? Is that what it is? 99.7. Or plus or minus 3 standard deviations of below and above the mean. Okay. The length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of a half an hour. A sample of size n equals 50 is drawn randomly from the population. Find the probability that the sample mean is between 1.8 hours and 2.3 hours. So again, what's the thing you have to decide here? The thing you have to decide is what standard deviation you use. Because again, you have a population that's normally distributed with a mean of what, 2? And a standard deviation of a half an hour. And you're trying to decide between 1.8 and 2.3, but what are you trying to decide this area under the curve is? The sample mean is between. So since you're talking about a distribution of sample means, you don't use a standard deviation of 0.5, do you? What standard deviation do you use? 0.5 divided by the square root of 50. So why am I using this? Because even though the population is normally distributed, I am interested in looking at the distribution of the sample means. Since I'm looking at a distribution of sample means, I have to use the smaller standard deviation. Okay, so what would this be? This would be a normal CDF with a lower limit of 1.8, an upper limit of 2.3, a mean of 2, and a standard deviation of what, 0.5 divided by the square root of 50? So normal distribution with a lower limit of 1.8, is that correct? And an upper limit of, was it 2.3? And a mean of 2? And a standard deviation was 0.5 divided by square root of 50. So normal 1.8, 2.3, 2, 0.5 divided by square root of 50. 0.9977. So the probability that a sample means between 1.8 and 2.3 is 99.8%. Okay, so remember from section 6.2 how to find percentiles. A percentile means that that many of your values is below that number. So if you score in the 90th percentile on a standardized test, that means you scored higher than 90% of the people who took the test. So to find the percentile K, you use the inverse norm. And you give the area to the left of K. So that is the percentile you're looking for. So the area would be 80 if you're looking for the 80th percentile. 40 if you're looking for the 40th percentile, etc. You use the mean of your population, but you use the standard deviation of the sample mean distribution. So you use that standard deviation, which is the standard deviation of the population divided by the square root of the sample size. In a recent study reported on the Flurry blog, the mean age of tablet users is 34, standard deviation is 15, sample size of 100. Find the 95th percentile to 1 decimal place. So what you're looking for, I have to draw a picture. Now, since we're looking at sample mean age, sigma will be 15 over the square root of 100. And we're looking for the 95th percentile. So what is this number where the area under the curve is 0.95? So you're going to do an inverse norm. The first number in your inverse norm is the area to the left. The second number is the mean. And the third number is your standard deviation. So this is your area to the left, I should say. Mean. And since we're doing a standard deviation, we're looking at sample means. That is our smaller standard deviation. Now, it depends on your calculator. And I'm not quite sure why they did this. My calculator allows you to find the area when the area under the curve is between two numbers to the left of a number or to the right. And the later calculators, they stopped doing that. I'm not sure why. So does your calculator have this? Mine's the only one. So if your calculator doesn't have this, it defaults that the area is to the left of whatever number you're looking for. So you have to find the area to the left, and it will give you that K value for the area to the left being whatever it is. So what do we have, 95? This calculator looks just like this. And I bought this. When did I start working here? Again, my mother passed away in 2014, so 2015. So I bought this like 5 or 6 years ago. Okay, what was my mean again? My mean was 34 years of age. My standard deviation, I know it's 1.5. I'm just going to type that in. So mine has the left in there. Yours might or might not, but what it has to have is the 0.95, the 34, and the 1.5. So the 95th percentile is 36.5. So 95% of the sample users, or the sample mean, is less than 96.5. All right. Last problem of the day. And I keep changing this problem because I don't like the way that it was written, so I keep changing it. But this to me is how you would use the central limit theorem. A retail company has a contract for their employees working in a product manufacturing and distribution, which says that they receive bonus pay if they can produce at least 102 products per day that are free of defects. On average, employees produce 100 products a day that are free of defects. So they're going to give them a bonus if they can produce 2 more items than average, free of defects. The standard deviation is 10. Samples from 50 random employees will be taken, and the quality will be examined for 1 day. What's the probability the employees get a bonus? So what you need to decide, all you need to decide is, what standard deviation am I going to use? Probably this is normally distributed. I mean, defects are normally distributed. With a standard deviation, a mean of 100 and a standard deviation of what? 10? And you're interested in, can they produce more than 102 defect-free? So what standard deviation do you use? Do you use 10, or do you use 10 divided by the square root of 50? Which one do you use? And why?
10, because it's not like
What's that?
10, because it doesn't say second mean anywhere in here.
Right there. That's why you know you're using the 10 over the square root of 50, because they're taking a sample and only looking at the sample. Kind of tricky, huh? But that's the reason you use this standard deviation, because how many employees do they have building doodads? I don't know, a lot. What are we building? We don't know, doodads. But they're going to sample 50 employees out of however many employees are making doodads. So they're going to sample them and look at the defect rate. What's the average number of defects in this sample of 50? And if it's over 102, they give everybody a bonus. Woohoo! So what's the probability they're going to get a bonus? So what you're interested in, what is the area under the curve to the right of 102? So this is going to be a normal CDF with a mean of 100. Oh, what's my lower limit? Sorry. What's my lower limit? 102? What's my upper limit? A really big number? What's my mean? My mean is 100. And what's my standard deviation? 10 divided by the square root of 50. Now it's going to be, it would be even worse if you use the population standard deviation. The probability of getting a bonus would be way smaller. So we're kind of glad they're using a sample. Okay, so we're going to do a normal distribution. Our lower limit was 102. Our upper limit is a really big number. 1 times 10 to the 99. The mean number of defective doodads a day was 100. And the standard deviation of my sample means would be 10 divided by the square root of 50. So what's the probability of them getting a bonus? 8%. Better than nothing. And that's where I'm going to quit for the day.